Okay, so sorry I had to make a video for class today. It um, came up kind of suddenly, this change of plans, and obviously I'd like to tell you about this last time we met, but I just didn't know until I was on the way home from work, actually. But here it goes. So I noticed as I was looking over the chapter, there's one thing we hadn't quite covered yet, and I'm kind of glad we hadn't covered it yet, because really solving equations or inequalities graphically is something that, well, to do it justice, you'd like to know something about how to make graphs, right? And we finally just did that today, so this is kind of a nice thing to circle back to now that we know a little bit about how to do graphing by transformations, right? So without further ado, here's the basic idea, is we can use graphs to guide calculations, or if you have technology, you could use the graph to find approximate solutions. Here's an example. Solve the absolute value of 2x plus 2 greater than 1. So of course we've already done this problem, but we've done this problem so far kind of in the dark, right? Just with an algorithm of sorts, and so I'm going to show you now how we can visualize it. Well, y is equal to 2 times the absolute value of x plus 1 by that algebra right there, and so then we can think about how to graph the absolute value function, right? We can think about, we take y equals the absolute value of x, we shift 1 left, that gets us to the absolute value of x plus 1, and then we multiply by 2, which stretches it vertically. And so it looks something like that, right? So how to solve that inequality? Well, to solve the inequality, we simply need points, right? On the y equals absolute value of 2x plus 2 graph, which are above that y equals 1 line. So you see those are coming from, if you look at this blue dotted line, the intersection of the absolute value with the blue dotted line, that's any of these points up there. Let me make them, I'll make them red here. These points up here are the points we're interested in, right? Because those are points where the absolute value is larger than 1. And, okay, so basically you see to the left or to the right, to the left of that intersection point or to the right of that intersection point, that'll be the solution we're looking for. So how do we find the points of intersection? Well, we solve 1 equals to twice the absolute value of x plus 1, which of course, by the usual algebra down here, gives us x equals to minus half or minus 1.5. And so in conclusion, from this graph, we can see that the solution to the inequality is minus infinity to 1.5 unioned with minus 0.5 to infinity. And so you notice that we didn't have to solve two inequalities, right? We just found the points of intersection and used the graph plus some intuition to solve the problem, right? So, you know, it's an alternative way to think about these things. Now, okay, so I'm going to kind of go kind of fast through these things. This video shouldn't last more than about 20 minutes. So what you're going to need to do is to pause and to work things out for yourself as you go, right? To get the best result from this, you want to take notes. And so you're not going to be able to take notes as fast as I'm going through these things, and I'm sorry about that, but I've kind of run out of time. Now, to solve y equals x minus 1 times x minus 3 times x minus 5 less than 0, of course we have a method already. We could use the sign chart. But another way we could do is to graph that cubic, right? To graph y equals to x minus 1 times x minus 3 times x minus 5, right? And then if we're looking for places where it's less than 0, well, we can see it. It's this part, right? And then this part over here is less than 0. And then what's greater than 0? Well, greater than 0 are this hump up here, right? And this guy over here, that's the part that's greater than 0. We don't care about that. So from the graph, we can see that the solution is, what is it? It's minus infinity to 1, not included, unioned with 3 to 5. There you go. We solved that inequality via the graph. So that's the, that's the graphical method. If you have a graph in hand, you can easily solve inequalities by just looking at the graph, if you know where the intercepts are, right? So of course, there are other examples like this one where we could look at a problem of equality. And in fact, I already kind of addressed this in your mission 2 with the links which eventually tempted you to Rickroll. And if you'd actually clicked on those, I know some of you couldn't because you had trouble with the Adobe and with your PDF reader. But if you did click on those, you'd see that I had graphs of 2 functions, and I was trying to get you to look at where they intersect as a means to find the solution. And so that idea is actually covered in your textbook in section 2.3. So I guess I was getting ahead of the story back in mission 2. Sorry about that. I'm still learning where things are in this course sometimes. But in here, I haven't given you formulas, right? So if you have a graph of 2 functions and you're trying to find the solution to f of x equals g of x just with the graph, all you can do is just do your best and go, aha, well that's where it crosses. There's one solution. There's another solution, right? And then there's another solution. So solution, well, to best approximation I can see here, minus 2, looks like 2, there's a solution, and this guy happens over here. Where is that? Probably 5.6, maybe 5.7. Well, we'll say 5 points, I don't know. You pick it, whatever, all right? Approximately there. So that's another thing we can think about. So that's just a little snippet from section 2.3. I thought we should talk about that a little bit. Now, most of what I have to talk about for this lecture concerns combining functions, or what you could say new functions from old. And so almost nobody has trouble with what I'm about to tell you. In particular, if I give you 2 functions, you can add them, you can subtract them, you can multiply them, and you can divide them. And to do that, you just add, subtract, multiply, or divide their values at the point, as is defined right here. And if the domain for f is a and the domain for g is b, then the domain for the sum, the difference, the product, it's just the intersection of the domains. The quotient, in order for that formula to make sense, we've got to rule out the points such that the value of g is 0. So the domain for the quotient can be a little bit smaller than the other 3. And here's an example. All right, so, oh, by the way, these definitions are so-called pointwise. The functions are defined pointwise. You might hear math people saying that past this point, so I mentioned that in passing. But here's an example. F of x is 1 over x minus 1. G of x is the square root of x plus 4. So let's think about the domain here. So that the domain of f is x is just real numbers not equal to 1, so I've drawn that in purple. The domain of g, well, we need that square root to take a non-negative input, and so from that we need minus 4 or bigger. See, when you plug in minus 4, you get 0, and beyond that, it works, right? From the perspective of transforming graphs, you could see the domain of the square root of x plus 4 as a problem from, taking the square root of x, which looks like that, and then moving it 4 units over here, right? So if you think about, that as y equals the square root of x plus 4, it's 4 left, right? And since we've moved 4 to the left, that gives us a domain minus 4 to infinity, because of course the domain of the square root function was 0 to infinity, right? So you can actually see the domain from that transformation of graphs section we just did too. There's so much you can learn from the graphs if you just start thinking about them a little bit. I personally find it very freeing to have 2 ways to understand something. And so for me, I'm always using sort of a synthesis of graphical thinking and what you might call algebraic or analytic thinking. Those two together, with those two together, we're much stronger. Diversity of thought, you could say. Okay, so the domain of f intersect with the domain of g. In this case, if you look at it, we're just basically going to go from minus 4 all the way out to infinity, except we got to lose that 1. So we go minus 4 to 1, union with 1 to infinity. And here's your formulas. The sum is the sum, the product is the product, and the quotient is you know, this divided by that, which ends up being this. The domain of the sum, the product, it's just that again. And then the domain of the quotient of the two functions. Make sure you can see that. Okay, you can see it, it's in frame. The domain of this guy is a little bit smaller because we have to exclude the -4. We can't divide by 0, right? Okay. So where were we? What page am I on? That was page 2. This was page 3. This is page 4. Come on. This is page 5. All right, so suppose f and g are functions, and we're given the f of 3 is 8, g of 3 is 5, and that's all we know. We don't have formulas, right? But we know that the value of f is 8 at 3, and the value of g is 5 when you input 3. Well, then we can calculate the sum and the product and the quotient just like that. Add, multiply, divide, there you go. So we don't always need formulas to calculate the sum, the product, or the quotient functions, right? And another thing we can think about is we can add graphs, right? If I have y equals f of x, if I have y equals g of x in the green, right? Then I can look at f plus g of x as the sum of these two graphs using, sometimes people call this the principle of superposition. You add the two graphs to get the third. This kind of thinking you have to do if you want to understand like the cancellation of sound. You know, like noise canceling headphones work off something like this. You know, you add the opposite curve to the noise and it makes it go to 0. Basically this graphical idea applied to sound waves, but anyway, so what should happen here is if we add together the blue and the green, we should get to the red. I don't know if I was completely successful in that, but like the red should be the same distance. It should be like, let me just make a picture here. This distance right here should be the same as that distance right here if I'm doing my job right, okay? Because to get the red, we take the green and then add the blue. You think of it that way. Whenever the blue or the green drops to 0, then the red is just equal to the other one. Like when the blue is 0, then the blue plus the green should just be the green because the blue is 0. Like over here, blue and green are both 0 at the same point, so red is also 0. And like over here, green is 0, so the red curve just is the blue curve again. Because again, when you do blue plus 0, you just get blue again. Again, blue plus 0 is just blue again. So, you know, is my picture exactly right? Probably not. But you know, if you want to look at these, it's kind of fun to go into something like Desmos or a graphing calculator and poke around, right? The point here is you can draw the red by adding the y values of the blue and the green. All right, so that's another way we could actually do graphically, especially if we had some graph paper and some more values labeled. You could get a lot of information that way. Okay, so the remainder of what I have to tell you today concerns the concept of composition. I think this is a little bit trickier. If you look at the textbook, they define the composite by the formula. Pretty much all the textbook says is, given a function f and a function g, f composed with g of x is f of g of x. And it doesn't say any of this stuff I have said about domain. Because the textbook realizes that the domain of a composite function is kind of complicated. And so they just kind of don't say anything about it. I have no common sense, so I will say something about it. And you can ignore me if you want, because I probably can't in good conscience test on this because it's kind of complicated. But basically the situation is this. The domain for the composite, it has to be a subset of the domain of the inside function. So, you know, a little bit of language here. F composed with g. So f is the outside function. And g is the inside function. And the reason we say that is the rule for the composite, right? Because f composed with g of x is by definition f of g of x. We feed the value of the inside function into the outside function, and that's how the composite works. So if you think about this formula making sense, first of all you need x in the domain of g, which I've made black here. And that takes you to g of x, right? Now if that g of x happens to fall inside the domain of f, which I've made this green, then you're okay, right? But you do need you need to have picked a point in the domain of g which happens to map to the domain of f. So a way to say that like precisely is this down here. You're taking the domain of g and you're intersecting it with the inverse image of the domain of f. Like the part of the domain of f which is over here, which is not inside the range of g, well that just goes back to nothing, so that doesn't affect anything here. And so I drew these little red arrows to try to indicate what that inverse image might look like. It's kind of like all these points are going back to over here. So this little smaller subset of the domain of g is actually going to give you the domain of the composite. Okay, digression over. Do not despair, please. Do not call your advisor. Do not give up on my class. I'm just telling you something that I probably shouldn't tell you, and I'm going to go back to the stuff I'll actually test right about now. Here we go. So f of x is x squared plus 1. G of x is 1 over this 1 plus the square root of x. I'm going to go ahead and calculate the composite in this case. So here we go. F composed with g of x by definition is f of g of x, which would be f of 1 over 1 plus root x. And so the way that works is we take and we square the input and we add 1. And there you go. I mean, we could simplify this, but that's perfectly fine. Now, if you didn't follow this, a way you could break it down further, and I say this is adding training wheels, you could look at f of u being u squared plus 1. Change the letter for the formula for f. And you could think about putting u equal to g of x. And then if we look at it, f of g of x is f of, f composed with g of x is f of g of x, which is f of u. But f of u is u squared plus 1. But again, u is equal to 1 over 1 plus the square root of x. And then we have to square that. We add 1. As you can see, we got back to the same formula by using this like variable change. So you can substitute a new variable. You can set g equal to the new variable. Another notation which has sometimes served me well in the past is just like doing this. You could look at it like this. I'll just squeeze this in here. Another way you could look at it is f composed with g of x. I mean, this is kind of cheating, but you could do like this in terms of notation anyway. So that's f of g of x. So we could just think of it roughly as f of g, right? And f of g, well, that would be g squared plus 1, right? But what that means in this context, and this is again, I mean, admittedly I'm abusing notation a little bit right here, and I'm sure some of my math colleagues would probably grimace at me even writing such a thing. But that's another notation you could kind of think through this thing in. But anyway, moving on here, f composed with g is not usually equal to g composed with f. It's important you understand which is inside and which is outside. It makes a difference. Like here's the calculation for g composed with f of x. We do g of x squared plus 1, which is 1 over 1 plus the square root of x squared plus 1. This function, that formula rather, is not the same as that formula, which means that g composed with f is not the same. It's not equal to f composed with g. Here's a few other examples. We can compose the function with itself, like f composed with f. It would be, x squared plus 1 squared, squared plus 1, like this, x squared plus 1, parentheses, squared plus 1. And, why not? I'll simplify it. That's x to the 4th plus 2x squared plus 2. But, again, unless I say simplify, you're not obligated to. G composed with g is going to give me g of 1 over 1 plus the square root of x, which is 1 over 1 plus the square root of 1 plus 1 over the square root of x. So that one's kind of fun. And just, before I forget, caution, fg is not equal to f composed of g. Very common mistake students make at this point is confusing the product of two functions with the composite. The product of f and g here is x squared plus 1 times 1 over 1 plus root x. This, of course, is not equal to, as a formula, f composed of g of x, which we had like back up there, right? These are not at all the same function. You have to distinguish between these. That little circle does not mean multiply, it means compose. All right? I think I forgot to number my page. We're on page 7. Wow, time flies when you're having fun. Again, time should be flying more slowly for you. You should have paused this video at least 2 or 3 times by now to stop and write things and to make yourself notes about what I said. Right? Of course, you are free to ask me questions by email or also in class when I get back, which hopefully will be, hopefully it'll be Tuesday actually, but I won't see you guys in class Tuesday, right? Here's another example. F of x equals to 2x plus 3. G of x is 1 over x. We can calculate f composed of g of x. So we do f of g of x, which here is f of 1 over x. So we take twice the input, the formula for f is 2 times the input plus 3, right? Here the input's 1 over x, so I do 2 times 1 over x plus 3. And, just as a point of fashion, I rewrite it as 2 over x plus 3, right? Fine. G composed with f of x is a really different thing, though, isn't it? So g composed with f of x is g of f of x, which here is 2x plus 3. Sorry, I skipped that kind of step here because, I don't know why I did it, but there's an in-between step here, which would be g of f of x, which gives us that, right? And then g of f of x, well, that's g. What does g do? G is the reciprocal function, right? So it flips the input, 1 over 2x plus 3. There you go. So we could also calculate f composed with x, f composed with itself, f of x, which is f of 2x plus 3, which is 2 times 2x plus 3, which is 4x plus 9. And this was so much fun, I thought, hey, I'll do it again. F composed with f of x, which would be f composed with f of x. We already figured out that was 4x plus 9, so plug that in there. And then, 2 times 4x plus 9 gives me 8x plus 18 plus 3, which is plus 21. And maybe you start to see a pattern here. If we compose f with itself twice, we get a 2 squared. If we compose f with itself 3 times, we get a 2 cubed. And I speculate that if we were to calculate the composite of f with itself n times, which you might denote like f to the n, then you would get 2 to the n times x plus some number. I don't know what the number is without more calculation. I can see that pattern from these examples, I should warn, this notation f upper n of x is not like universally, this is not a standard notation, and there is some, let's see, how can I say this? Certainly like sine squared of x you'll talk about next semester, and like just, comment, let me make a comment here, just, something to tuck away for later. Me writing that is not awesome because sine squared of x, what that means is sine of x squared. So, this notation isn't quite right in that regard, but, well, anyway, I'll say more about this when we talk about inverse functions, but there's a unfortunate badness to this notation that comes up when we look at certain other functions. I'll talk more about that later, and let's not talk about it right now. Anyway, another example, and this will be the final one. Oh man, I see I've gone 5 minutes over. Is if I compose a linear function, with itself, like mx plus b with lx plus c, then something kind of neat happens. We get, f of Lx plus c, which is m times Lx plus c plus b, but if you multiply that out, you get mLx plus mc plus b. So if you look at that, the slope is ml, and the y-intercept is this thing over here. But the larger point is that the slope, right, is a product of the slopes of the functions, which are the linear functions, which are composed. That's pretty neat. So the composite of linear functions is again a linear function whose slope is the product of the slopes of the composed functions. For what it's worth, this is actually the source of the chain rule in calculus. So I'll just tell you that, and if you come take Calculus 1 with me sometime, then I'll explain that to you in more depth. Anyway, again, sorry I couldn't be with you today. I know it probably breaks your heart, but if it's any consolation, I'm suffering with much traveling this weekend. I'm just kidding. I shall be back soon. Again, sorry for the super short notice on this one. Bye, guys.